Hi class. So this is the fourth way in which we can get air to rise, and this will complete the notes for chapter 6. So the fourth way in which we can get air to rise is through the process of convergence. And so one way that we've talked about this fairly extensively is in the center of a low pressure. So we know as we look down on a low pressure, as we would on a weather map, we know that the air flows counterclockwise and inward towards the low pressure. And it converges in the center of low pressure, hence the convergence. If we look at this from a profile standpoint, so if we're looking at the horizon, and there's our horizon, and if we were able to see the low pressure on the horizon, that air would be flowing counterclockwise and inward, and when it meets in the center of low pressure, it's going to rise. Okay. All right, so that rising air is the first thing that we're going to talk about. And again, we've talked about this pretty extensively in these videos. Repetition is good. And as the air ascends, due to the convergence, the pressure is going to decrease. When the pressure decreases, the air expands. When the air expands, the density of the air decreases. And when the density of the air decreases, the temperature of that air is going to decrease. And as the air rises, as long as it is unsaturated, the temperature will decrease at the dry adiabatic lapse rate, which is 10 degrees Celsius for every 1,000 meters that it rises. Okay, so in the center of this low pressure, as the air is rising and all of these processes are taking place, there might come a point, and likely will become a point, where the air becomes saturated and you begin to condense the water vapor into cloud droplets. Okay, and that takes place at the LCL, the lifting condensation level. Okay, and so at the lifting condensation level, that's where the saturation occurs. That's where the relative humidity is 100%. That's where the mixing ratio is equal to the saturation mixing ratio. And if you know the mixing ratio, you know the dew point temperature. And if you know the saturation mixing ratio, you know the temperature. So if mixing ratio is equal to saturation mixing ratio, then the dew point temperature is equal to the actual air temperature. This is where condensation occurs, condensing water vapor into liquid water droplets. Okay, so condensation occurs at the LCL. And when you condense water vapor into liquid water, you are going to release heat energy in that phase change of water from water vapor to liquid water. You're going to release 600 calories of energy per gram. You're literally releasing heat energy into the atmosphere, warming the atmosphere so that as the air continues to rise, it's still going to cool, but it's going to slow down the rate of cooling, okay, because we've reached saturation and we switch to the moist adiabatic lapse rate, which has a range of values. We've been using 5 degrees C per 1,000 meters. But that can vary between 5 degrees C per 1,000 meters and 9 degrees C per 1,000 meters. The soupier the air, the more heat energy is going to be released when condensation occurs. So that's going to slow down that rate of cooling the most. If you've got a place like the polar regions where the air might be saturated but there's not as much water vapor in the air, then that moist adiabatic lapse rate might be as much as 9 degrees C per 1,000 meters. Okay, so this was the last of the 4 ways to get air to rise. I do want to, you might be thinking to yourself that, wow, that all sounded exactly the same. And to be honest with you, it is exactly the same. The process is exactly the same. It's just the way in which we get the air to rise in the first place. So going back to our diagram of convection, we got the air to rise because solar radiation warmed up the surface and caused convection to occur. Solar radiation was absorbed by the Earth's surface, made the Earth's surface warmer, warmed up those air parcels, so they were less dense. Being less dense, they rose through convection. Okay, and then when the air started rising, all of those steps took place. If we are talking about orographic lifting, okay, all the steps are exactly the same. The only thing different is how does the air begin to rise. In this particular case, we put a barrier in the way, a barrier such as a mountain. That caused the air to rise. Once the air starts to rise, the process is exactly the same, okay? If we have a front coming through, okay? We have air rising because of density differences, okay? In this particular case, cold, dry, dense air is forcing warm, moist air to rise. Once the air starts to rise, the process is exactly the same. The only thing different is how do you get the air to rise. In this case, it was frontal wedging. Okay? And then the fourth one, convergence. Again, the only thing different is how do you get the air to rise. Air converges into a central point, in this case a low pressure system. There it's forced to rise. Once the air starts to rise, all the processes are exactly the same. So again, the process is exactly the same. The only thing that's different is how do you get that air to start rising. That's it. That is chapter 6. Okay, so if you have any questions, let me know.